Good evening, Math 30-1. Today we're moving on to the second section of our polynomial functions, titled the Remainder Theorem. So at the beginning we still have our definition of what a polynomial function is and the three requirements in order to be a polynomial. Now before we start, I'm going to do a quick review of long division. And as you may guess then, long division is going to have some impact on what we're going to do today. So going back to a little bit of a review of what you have done in the past. I'm going to start with this first question here. We have 7, and we're dividing it 102. First thing I want to identify is you're going to see on your notes that the 7 is what we call our divisor. The 102 is our dividend. And when we get our answer, we're going to find the quotient, and we're going to focus on dividing it to the point where we're actually going to have a remainder, like you've done in the past. So first off, 7 doesn't go into 1, but 7 goes into 10 one time. So we can write our 7 down here. Next, we take 10, subtract 7, gives us 3. After the step, we carry down our 2. And now we have to consider how many times 7 goes into 32, which is 4 times. 7 times 4 is 28. And again, we subtract. Now I'm going to actually write the subtraction here so we can see what's going on. If we now go 32, subtract 28, gives us 4. And we now have our remainder. So our quotient is 14, our remainder is 4, and we're done. We're done the question. So if you now go back to our second one, what you should find is that then if we take 243 and we divide that by 4, your answer will be 60 with a remainder of 3. So what you should find with this, with question number 2, question number 2 is going to have an answer of 60 with a remainder 3. And question number 3 is going to have the solution of 121 with a remainder of 2. Okay, you can double check that for me, but following our long division process, that should be what you would end up with. So we're now going to take this concept and we're going to apply it to our polynomials. Specifically, we're going to follow a definition outlined here below. Here, I'll enlarge it a little bit for you so you can see it better. What we're going to say here is we're going to take our polynomial, and we're using p of x to represent our polynomial. We're going to divide it by not just a regular number or a whole number like we did in these long division examples. We're going to divide by what we call a binomial. Bi means 2, and so we have 2 terms, x and a. So we're going to take the polynomial, we're going to divide by this binomial, and similar to what we got up above, we're going to get our quotient. So I had a quotient of 60 in example 2. In the case of our polynomials, our quotient is going to be a function itself, so we're calling it q of x. And then similarly to the long division examples above, we have a remainder. And our remainder in these examples is going to be, we represent by r, and it's still going to be divided by x subtract a. In these examples, we could technically say that our remainder here is also still being divided by whatever our divisor was. But we don't generally identify that. We just leave it as a remainder. So we're going to now try and do this with a polynomial. Now I'll do it here first on the sideboard so that you can see what I'm doing. And then I'm going to demonstrate specifically all of the kind of rules. So we're going to take our x squared. Let's go back to my pen function. We're going to take x squared plus 7x plus 2. And I'm going to divide that by x plus 2. Okay, now the focus of these questions, when we're looking at these divisions or these this long division process, we are going to try and focus on whatever our first term is. This first term we are going to compare to the first term of our polynomial. And we need to think how many times, or what I have to multiply this x by to get x squared. The answer to that is going to be an x. And I'm going to write it over top of the other x term, just so I can get everything lined up. Now, similarly to when I did long division, after I've found out what I'm multiplying by, I have to take this x and multiply it by everything in the front. So this x plus 2 is going to be multiplied by my x. So I take that x, multiply by x, and it gives me x squared. I am now going to take my x again, that is in my divisor, and I multiply by a 2, and that gives me 2x. Now I'm going to put this second term here in a set of parentheses, because just like we did with long division, I'm now going to subtract. X squared subtract x squared gives me a 0. 7x subtract 2x gives me 5x, specifically a positive 5x. And then like we did in the last example in the long division, we have to carry our 2 down, so I now have a plus 2. Next step now is, instead of focusing on any terms up here, I'm now comparing this x term to this 5x right here. Okay, so I have to think, what do I have to multiply this x by to get it to equal 5x? And the answer to that is going to be a 5, specifically a positive 5. So I'm going to write positive 5 above, and I take my 5 now and multiply it by everything, okay, in my divisor. So 5 times x gives me a 5x. 5 times 2 gives me a 10. And again, I'm going to put this in a set of parentheses, and I'm going to subtract. 5x subtract 5x is a 0, and 2 subtract 10 gives me a negative 8. Okay, so what I should have here now is that I have a divisor, or quotient, of x plus 5, and a remainder of 8. So if I were to write this in my polynomial notation, which I have indicated in my notes, okay, I would scroll down, and I would say that my x squared plus 7x plus 2 divided by x plus 2 is equal to x plus 5. Now my remainder was a negative, so I'm going to subtract 8, and it's still going to be divided by whatever my original divisor was, which is x plus 2. So if we go back to the notes, we can double check that again. So steps to solve again. Okay, notice how I have a typo here in my notes. Okay, this should say an x plus 5 in my quotient. Again, it's also down here, so double check here on the right hand side, it says x plus 5, not x subtract 5, so there's a typo here too. But steps to solve. The polynomial must be descending order of powers. Okay, so again, if we look at this x squared plus 7x plus 2, each term is in a descending power. First the power is 2, then the power is 1, then the power is 0. Any missing terms are to be filled in with a 0 placeholder. If I didn't have a exponent, for example, let's say like we have in this your turn question down here, question number 2, when I do that term, I'm going to have to put in a 0 x squared. I have to fill in the place because I have to have descending orders with a cubed, a squared, 1, and a 0. Okay, so in the your turn question number 2, which I will leave for you to try, you have got to put in a a 0x squared. So actually, let me demonstrate that here. Okay, what we would do here is, again, we would have our divisor of x plus 4. We are going to do a long division process. And you would put an x cubed. I don't have an x squared, so I have to put in the placeholder plus 0x squared, because you have to have that power there, plus or subtract by 20x plus 8. This is what I would write in order to do my long division for this question. Okay, so that 0x squared is a placeholder. Step number 2, only the first term is used when doing the division. So we only focus on the x, and I start off with my x squared. Okay. Now, whatever I choose, so when I chose my x, that x had to be multiplied by my entire divisor, so that's for step 3, giving me my x squared plus 2x, and then I subtract, leaving with just a 5x, and then again I carry my next term down, just like we did with the long division. Also, make sure to identify, okay, your restrictions here. So I have x cannot equal -2. Okay, that is only restriction for when we're actually doing the division process. You're going to see later on that we're going to use that number in another scenario, similar but not quite the same. But in this case, that is a restriction. We cannot have x equal to -2. If we did, we'd be dividing by 0 in this remainder term, and you can never divide by 0. So I'm going to leave you to try those 2 your turn questions, and then we'll move. You can ask me about them tomorrow or the next day after you've tried them and give them see how you did. So now we're going to move on to a process called synthetic division. Synthetic division is very much like long division. It's a little bit shorter. It's, as defined here, a method of performing polynomial long division involving a binomial divisor. Okay, so what we've just done, that only focuses on the coefficients. Okay, so I've demonstrated it right here to the right. Here's my polynomial. Okay, it is this x cubed subtract 2x squared subtract 33x plus 90. In synthetic division, I only focus on the coefficients. Okay, so instead of just having this answer right here, I'm going to move that away, and I'm going to do it on the side here. Okay, so let's add another page. And let's do this question here on the side. Okay, so starting off, I'm just going to create a little bit of a box. Now inside my box, I'm going to put the coefficients on my polynomial. So there's a 1 in front of the x cubed, a -2, a -33, and a +90. Now I don't have to put the positive. Whenever we don't have a positive, we just assume that it's positive. Apologize for the poor writing here. And then on the left side of my box, I'm going to take that the constant term from my divisor. So in this case, it's my -5. So only the constant term. Now, step 1 is I'm going to take this 1 and I'm going to carry it down. You don't necessarily have to put an arrow, but I'm going to demonstrate. And I get a 1 here. That's the first step. The first term always gets carried down. Second step, I'm going to take my -5. I'm going to multiply it by this 1. And the result I put right below the next term. So -5 times 1 gives me a -5. Now, similar to what we did before, I'm going to do a subtraction. So I'm going to actually write a little bit of subtraction here that you know what you're doing. So I have a -2 subtract a -5. Remember that when you subtract negative, it's the same thing as adding. So -2 subtract -5 is like saying -2 plus 5, which gives me a +3. Following this pattern, I'm going to take my negative 5 and multiply it by 3, giving me negative 15. So negative 33 subtracting negative 15 is going to give me a negative 18. And then the last step, again, take negative 5, multiply by negative 18, and that's going to give me a positive 90. So when I do this final subtraction here, okay, 90 subtract 90 is 0. Now, this last term, I'm just going to put kind of box it off. The last term here is very special. The last term always represents our remainder. Okay, so this is our remainder here. Ugly R. So following that process, we can solve for the remainders of our division process, but in this case we're only focusing on coefficients instead of the full variables. So let's compare that again to what I had down here, and you'll see that they are the same. So step 1 was write only the constant term of the divisor and the coefficients of the dividend. So the negative 5, the 1, the negative 2, negative 33, and 90. I brought the first term down, then I multiplied 1 by negative 5 and subtracted. Multiplied 3 by negative 5, record the product and subtracted. Multiplied the negative 18 by negative 5, record the product and subtracted. These three terms now, they represent the coefficients of my quotient. So 1, 3, negative 18. My remainder was 0. The negative 18 represents my constant term. The 3 is going to represent my first variable, so the degree 1, so 3x. And then the 1 is now an x squared. What I want to note is recognize that the original polynomial was a degree of 3. Our quotient now is a degree of 2. Every time you do this process, your quotient is going to have one lower degree than your original polynomial. Okay, so it always decreases. So what I can now write as my, using a division statement, I can rewrite my polynomial here as an x subtract 5 multiplied by x squared plus 3x subtract 15. So this here demonstrates one of my factors. Okay. I was able to simplify that third degree polynomial into a binomial and a second degree polynomial. And so they're factors of each other. So I'll let you take a try on that using this fourth degree polynomial and the binomial. Again, if you have any questions, if you want me to double check, we can take a look at it in the next day. Moving on then to the focus, the remainder theorem. Everything has been so far focusing on solving for the remainder. Now there is actually kind of a shortcut for this, and it's what we call the remainder theorem. One way of solving for the remainder is doing what we just did with synthetic division. So if I took this third degree polynomial and divide by x subtract 1, I can find my remainder is 3. What I want to demonstrate is that if I take what we would consider to be our restriction, okay, saying that x cannot equal 1, instead of actually dividing, okay, I'm going to take that same number and plug it into the function. Now this isn't going to cause any problems because by plugging it into the function, I'm not actually doing a division. So right now, saying that x equals 1 is not infringing or is not breaking any rules. Okay, so testing x equal to 1 is not breaking any rules with the restriction. Okay, it was only a restriction when we were dividing. So what we're doing is we're solving for the remainder without dividing. So it's okay for me to use the number. So I take x equal to 1, I plug it into all my x values into my function, into my polynomial, and look at the answer I get, 3. Okay, the answer ends up being the same as my remainder. This happens in every single case. So if a question is ever asking you to solve for just the remainder, you do not have to follow through with the long division or synthetic division process. In the assignment and on the test, you will be asked to do some synthetic division or long division. But if the question is only asking for the remainder, all you need to do is determine the x value that you're going to test and that is based off of your divisor, okay, such as up here, which is x subtract 1. You take that x value, you plug it into your polynomial, and you solve for your answer. Okay. So when a polynomial, p of x, is divided by x subtract a, the remainder is solved for by just taking p of a. Okay, so whatever that a value is. Okay, recognize that this is defined with a subtraction sign. Okay, so think x subtract a, then x is equal to a. If it was saying x plus a number, okay, then you have to switch. Our x value would be a negative. Okay, so that's what our remainder theorem states. So we're going to test it out here. Example number 3, we have a polynomial and we have two divisors that we're going to test. In this first case here, our a value would be 2, so we're going to test the polynomial when x is equal to 2, or p2. When we plug 2 into our polynomial, okay, we follow order of operations and we simplify, and we find out our remainder is 1. You would get the same thing if you were to take this polynomial and actually divide it by x subtract 2, if you were to use either synthetic or long division. Similarly, with b here, x plus 1 tells us that the x value we're going to test is a negative 1. So if it helps you remember, just think that we have to switch the sign to actually find the x value we test. So we take a negative 1 and we plug it into our polynomial, and we find out we have a remainder of negative 11. Building off this concept now, we're going to go into this fourth example. And again, you can write the notes down right away, but we're given a polynomial here where we don't know the coefficient of one of the terms. Okay, we're just putting a k in there. It's just going to represent our coefficient. We're going to say that we're going to divide by x subtract 4, and we're told what the remainder is. So in this case, we want to determine that coefficient k. Now we know that if we were to take x equal to 4, okay, which we're told by the divisor, and plug it into our polynomial, our remainder would be 30. So p4 is equal to 30. So what we're going to do is we're going to actually take that number 4 from our divisor, plug it into our polynomial, as I did right here. It's equal to 30. We simplify. So 4 cubed is 64. 4 times k is just negative 4k. We have to subtract 6. I rearrange it, and I find out that negative 4k is equal to negative 28. And so when I divide both sides by negative 4, I find k is equal to 7. Again, I've seen this question on some diploma exams in the past, or similar questions. I am not sure whether I have it. I don't remember if I have it on my test or on my assignment, but it's something to be aware of. The remainder theorem is very straightforward. It's going to help simplify your work, and again, if you just focus on what the question's asking, if the question just asks for a remainder, use the remainder theorem, or if it gives you a remainder, use the remainder theorem. You do not always have to follow through with synthetic or long division, but you will have to for the assignment. I'm going to ask you to do those two just so that we can learn the process and improve with that. So again, your assignment is due on Friday, October the 4th. This should say 2013. So feel free to work on that and ask me any questions if you're unsure. Thank you very much and have a good day.